Okay, good evening, Professor DBJ de los Reyes. Okay, my topic for this session will be a long video format topic, and this is on AC machines. And we are now on lesson number 46. We are almost done with transformer. Okay, let's proceed for the topic for tonight. The subject matter for tonight will be another topic. This will be alternating current machines, lesson number 46. This is still on the study of transformers, and we are now on the so-called delta to Y or Y to delta connection. So the title of the topic for tonight, it will be another example problem on the delta and open delta connection. This is another variation of problem, delta delta, then later on it becomes delta or open delta because one of the transformers was taken out for repair. So the problem must have to operate in the so-called open delta. So the title of the topic will be from delta to open delta connection. So at least we know how to compute what you call this, the requirements if there is a conversion from delta or closed delta to open delta. Okay, I will try to read the problem. 3 transformers are rated 100 kVA and are connected in delta. 3 transformers. Okay, the rating of each is 100 kVA. And they are connected in delta. Okay, supplying a load of 160 kilowatts at 0.8 power factor lagging. Originally, the connection was delta-delta, and the 3-phase load that is being supplied with current on the secondary is with the total true power rating of 160 kilowatts. The power factor is 0.8. This is lagging. Lagging maybe it's a motor loads. Okay, it comprises of many motor loads. Okay, I will try to continue. If one of the transformers is removed for repairs, determine the size and kilobar of the capacitor needed. So the remaining transformers will be loaded to 95% of rated capacity. So if one of the transformers is removed, we remove this one. So it will be something like this: open delta on the primary, open delta on the secondary. Okay. The problem is asking what will be the kilobar. The kilobar of the capacitor, which must be connected on the secondary. Okay. So the remaining transformers, meaning the remaining open delta transformers, will just carry 95% of rated capacity. So they will not be overloaded. The addition of the capacitor will decrease the load on the transformers, because for a capacitor, the what they call this, the reactive power is actually upwards, and the reactive power of the load is actually downwards. So if we try to combine these two here, it will be a lesser value such that the overall load of the open delta will just be 95% of its rated capacity. So it seems this is a problem also in connection with the so-called power factor correction. We are not correcting the power factor, but the introduction of the capacitor, okay, will lead to the so-called elimination of some of the currents. So the remaining open delta will just be rated to 95% of rated capacity. So meaning to say, this kilobar of the capacitor will help the open delta to just carry 95%, and it will not be overloaded. Okay, let's try to bring out the figure. The original connection is a closed delta, 100, 100, 100. Okay. On the primary, secondary, it's also 100, 100, 100. And the total load originally, a three-phase balanced three-phase load is 160 kilowatts, 0.8 power factor. If we try to compute for the total apparent power factor of this, it will be 160 over 0.8, and this should be 200 kVA. The total apparent power of this power of the load is 200 kVA. Okay, so at least we know how much is this one, so we could compute. We could compute for the what they call this the total apparent power rating that could be carried by an open delta. So we must have to bring out the relation of the apparent power of the closed and open delta. At least we must have to bring out this one. That's why in the formulation of the equations, I brought out the relation of the apparent power of the closed delta with regards to the closed delta with regards to open delta. And actually, that relation is actually given by this relation here. Right? If we try to compute for the total apparent power rating of the closed delta, the total apparent power that could be carried by the closed delta will be the individual ratings of the transformers. Since originally there are three, okay, so it should be 100, 100, 100, so this is 100 times 3. Okay? And if we now try to revert or change the connection from a closed delta to open delta because one of the transformers is removed for repair. Okay, this is open now, this is open. If we try to compute for the total apparent power that could be carried by this, it is actually given by this equation here. It is only 57.735%. That was one of the annotations on the comparison of the open delta and closed delta from our previous lesson. So this is 100 times 3. Why times 3? There are 3 originally, right, for the closed delta. So to get the total apparent power that could be carried by an open delta, it will be this closed delta apparent power divided by square root 3, or only 50%. So 100 times 3 over square root 3, or this should be 173.2 kVA. So the original 300 kVA was now reduced to 173.2 kVA. This will now be the total apparent power that could be carried by these two here. Okay, they are slightly they just give slightly less apparent power because of the third one is actually missing. It's only 173.2 kVA. So this is the normal load that could be carried by these two here. And the problem says what will be the kilobar needed to just load the open delta to 95%. So if we try to bring out the percent loading according to the given problem, the open delta transformers will only be loaded to 95%, so it will just be simply 0.95 times 173.2. So it will just be simply loaded to 164.84. For these two windings, the problem says they should only carry this one here. Okay? Okay, let's try to bring out the kilobar of the capacitor needed. If we try to bring out the power triangle of the three-phase load, it is this, right? Apparent power will be 160 kilowatt over 0.8. This formula here emanates from power factor equal to kilowatt over kVA. So if we try to compute for kVA of this load here, we need the power triangle of this one. It should be kilowatt over power factor, right? Or we put this one over here when we put power factor underneath. So it is this 160 over 0.8. So the total kVA of this is 200 kVA. If we try to bring up the power triangle, this is 200 kVA. Total true power is 160. If we try to compute for the reactive consumption of the motor loads on the three-phase load, it will be the square of this minus the square of this, then take the square root. It should be 120 kilobar. Okay. So to compute now for the kilobar of the, this is now the power triangle of the capacitor. It's a pure reactive power, it is upwards. We combine this power triangle of the capacitor to the power triangle of the load. So the power triangle of the load, I will try to remove the hypotenuse now. It will be this 120 here. This should be downward, right? This should be downward. Downward. It's lagging. And this is the true power. Okay? It is with respect to the zero axis. So if we now try to combine this one here, the power triangle of the load plus the needed unknown kilobar of the capacitor needed, okay, the true power will be 160 plus 0 or simply 160 kilowatt. And the overall reactive power will be this downward here minus upwards. The downward is 120. Upward is, this kilobar of the capacitor is upward. So this one here will be the difference of 120 minus this. 120 minus C kilobar. So actually in here, we are given a right triangle in which the only unknown is this one. C kilobar. Right? And the vector sum of this 160 plus this here should equal to the loading required. The loading is this one, 164.84 kVA. It will just only be loaded to 95% of 173.2, which is 164.84. So the vectorial sum of this plus this should be 164.84. So it seems we go back to the so-called study of trigonometry. We are given a right triangle in which all the sides are given except for this portion here, because this portion is the one we are looking for. So using Pythagoras principle, I'm ising on 164.54 square equal to the square of the hypotenuse should be the square of this side here, which is 160 square. And this side here is the difference 120. 120 is downward, this is upward, so it's actually this one is the difference. Okay, 120 minus kilobar quantity square. If we try to compute for this, we transpose this to the left, then we will take the square root of both sides. So 120 minus C kilobar equal to the square root 164.54 square minus 160 square. And if we try to bring out the equivalent of this, it is 38.38. So if we try to compute per kilobar, we put this one on the right, then we transpose this on the left, then we try to rearrange. C kilobar now will be 120 minus 38.38, and C kilobar will be 81.62 kilobars. So the needed kilobar of the capacitor, which must be connected across the three lines on the secondary, for the open delta to be just loaded to 95% will be 81.62. And if we try to divide this by 3, C kilobar per line is 27.2 kilobar. So we must have to place here a 27.2 kilobar. And so with this one and this one. Across line 1 and line 2, it's 27.2 kilobar of a capacitor. Across line number 2 and number 3, it should be 27.2 kilobar also. And line number 1 and number 3 should also be 27.2 kilobar. The total is 81.62 kilobar, such that the open delta transformer will only be loaded to 164.84 kVA. Okay, that's it, guys. This is a good example of the so-called delta to open delta transformation, plus the additional thing, the kilobar rating. The kilobar rating is actually needed to reduce the current, okay, that could be consumed on the secondary, since the open delta will only deliver not so much power because of the other transformer which is being repaired. Okay, good evening from Los Angeles. Professor David J. Rosre.